All right, what is up, everybody? How are you doing? Nightshade Dude, hello. Hello, other people watching. This is episode 3 of CSGFlix. We're building a video streaming service from scratch. And for those of you who missed out, and believe me, you missed out. Wednesday session was awesome. but we basically ended with a version of this video encoding that we built from scratch, which had video and audio that was encoded in JSON. So it's very accessible JSON. It's something that's incredibly easy to parse and the kind of thing that you can probably live code. But we're going to get to some binary later. I'm gonna mention a little bit about that as we go on. But one of the constraints, I guess, that we have with how I'm building this is I want to make sure that despite the fact that we're doing things in JSON, it's easy to inspect, it is a format that we're going to be able to repack in binary. So I'm sticking to byte sizes and some other stuff that we'll get to a little bit later. But for now, it's JSON. I don't think there's ever been a video encoding done in JSON. So you watched it here first on Twitch. Great. Well, what do we have in store for today? We have, so the video and audio are working. We're playing it in the browser is where we sort of left off last time. And now we are going to try to compress it. So I title this The Art of Throwing Away Bits. So this is kind of a fun exercise because we want to try to throw away as many bits as we can while still retaining a really high quality picture and high quality audio. Now, as you saw in the earlier stream, we already started by reducing bits in some rather drastic ways just to get it to be more manageable under the the sizes we were dealing with. But today we're going to talk about some compressing techniques, and they're going to broadly fall into a few categories that we're going to cover as we start whiteboarding. So I'm not going to go too deep into any one of those. Like I've said before, any one of the topics that we're covering in these 8 topics to build a video streaming service from scratch is something you could study. You can really go down the rabbit hole. You can do a lot of CS work. You could do PhDs. You could work in the corporate world for a while on any one of these topics. So we're just trying to build enough to get a full end-to-end service, but possibly in the future, if there's interest, we might start going down some of those rabbit holes. But for today, we're going to try to keep our compression nice and simple. So let's see if that's doable. So without further ado, let's do that. All right, I've got my glove on. So we are in episode 3. Yeah. All right, and we have a title here from MyPaint. Thank you. This is CSGFlix, and I even left it in the same color as the end of last stream. And hello, Stupak. How are you doing today? So today we're talking about compression. I'm going to go very uppercase on this because it's a very big topic, but it needs to be a very small topic. Ha ha ha, puns. Okay, Okigan, how are you doing? And welcome to the stream. So, what are we going to talk about? Well, compression really falls into 2 major categories. And that's, there's a lot of techniques that you can use. It's a very large field, but it really broadly breaks down into techniques that are lossless and techniques that are lossy. So what's the difference between these two? This reproduces exactly whatever you compressed. So yes, we're not doing ML today, Stupak. And sure thing, Nightshade Dude. So this basically says, like, if I take a file and I compact the thing and I make a small file, I need to be able to expand it back and get exactly the same original file. So if this said one thing, it had better say exactly the same thing after it's, in its compressed form. So this is one set of techniques that we're going to use. Now, this fortunately is very well studied, so I'm not going to go too deep into this. There's a lot of information available on it, but it does apply to what we're going to do today. So to get a little bit of a taste of this, we're going to use a relatively simple version of this, which is based on something called RLE. So we're going to be doing some RLE today because I think it's something that we can get through relatively quickly, and I'll point you at some of the other techniques. Oh yeah, and by the way, kind of to Stupak's comments, lossless compression, when you get exactly the same thing out, that's similar to something like zip. Okay, so that would be like zip or gzip or bzip2 or lharc if you're back in the day, or whatever. So there's a whole lot of these, but the important thing is that I end up with exactly the same thing that I started with. So I had, even after compression, I need to get back bit exact version. And whatever it is up here, it had better be exactly the same down here. Lossy, on the other hand, is about throwing away. So lossless, we're just make small, but exact. So we're able to reproduce from our original all the way back to our original, even if we throw it into a small intermediate format. Lossy, on the other hand, is about not exact. So this is kind of an interesting field, which is sort of more of what can we throw away when we actually go and compress this thing. So I'll pick a different brown, but so we take our file and we make it really small, and when we expand it again, we get something similar to the original. So it's not exactly the same as the original, but it's something, it should be something fairly close to it. And yes, to Stupak's comments, this is something that's more like a JPEG. So JPEG would fit into this category. We're going to use some LSB tricks that I'm going to go over later, and we're going to cover some stuff in this field. We're going to start with, again, something relatively simple. So we're going to take bits and we're just going to throw them away. This is all about having a trash can, and yeah, that's our trash. So we want to take some of these bits, throw them away, and we're never going to get them again. Actually, they're gone. So, but we want to try to get something close to the original that is as small as we can kind of get. And hey, what's up, Primogen? How are you doing? MP4, don't be ignorant. Okay, well, yeah, this would include things like MP3s and MP4s for, this is just straight on the audio side, and this is actually a packing format, so the equivalent audio would be like AAC. That goes in here. AL1 is something that comes a bit later out of a different generation, but yes, he is correct. This is something that fits into kind of the lossy camp. Okay, so here we have to be really careful because we are losing quality. So this is really all about what quality can we lose that still maintains the same visual image. So if we see our dude and he's chilling out in a scene, then we want to say like, okay, maybe we don't need as much detail over here because it's mostly black, as we do around the character, maybe the face. Like we want a lot more detail here where people are going to notice it versus like, here where like if this black is like one shade of black and this black is like just a slightly different shade of black, like no one's really going to care too much because we're not worried about making an exact reproduction. If we were, then we would be using lossless techniques. And for images, that would include things like Targa files, and again, this other stuff, which is actually, they're all using versions of Lempel-Ziv and Huffman encoding. So we're not going to go this far down the rabbit hole, so let's not go there. And look at that, 7 people were there. Yep. No bots. I think actually mine's showing 10, but I've come not to believe whatever the view count is. Mm. Okay, so what we're going to do today is we're going to try to do some version of a lossless and some version of a lossy codec. So what I want to play with, let's go to I don't know, what are we feeling? A little more pink. So what we're going to start with is well, I mean, again, these fields are really deep, and I want to try to keep the implementation as simple as possible so that we can, reasonably get it done in a reasonable amount of time. So why don't we start off with a few easy things to kind of warm up. So the overall plan that I'm going to follow, and I'm not sure our plan should be pink, that might be a little too much, is we're going to first do a lossy technique. So this is lossy, and that's going to be scaling. I like to joke about this one a lot because, this is exactly what you see when you're watching a movie and they say enhance, enhance, enhance. And the trick here is we basically take a large picture, we make it a small picture, and then we blow it back up to being a big picture. So this is actually a little bit more complicated than it looks, but fortunately, since we're working in the browser, we get it pretty much for free. So I think it's a pretty good place to start. And the way we're going to do that was basically we're just going to play with the width and the height. So we're going to say, hey, browser, do some magic for us and take this image and resample it down to this size. And then later on, we're going to, so this would be in the encode phase. And later on, when we're playing it back, let's, resample it again and expand it. Now, that's going to cause things like, if I had some really nice detail here, that's going to turn into like one block here. But when I expand it again, I'm going to get kind of a grayed out area here. So I'm not going to have the same visual fidelity that I had in my original image, but I'm going to get roughly the same idea, and I can get it relatively easy. So we're going to start there. That's actually going to save us quite a bit of space. One of the metrics we're going to watch is sort of like, if we had things perfect, how much smaller can we make the encoded file and still keep good quality? So our game is like small file, but really good quality. So that's what we want to do if we're doing a good job. All right, so great. We're going to do some lossy scale stuff. We already touched on in the last episode. I'm just going to quickly go over it, but we basically talked about deltas, and that was this is really a lossless technique. And in this, we were taking we were looking at the scene and we were saying, okay, from one frame to the next, most of the scene doesn't change. Like say in our example, we had a guy who was waving. So this frame is like his hand's just a little bit higher than it was in this frame. But like the vast majority of this scene is exactly the same as it was in that scene. So we can actually just take this part and encode it, and that's our delta, and basically just reapply that. And we can end up with exactly the same image that would have been there if we hadn't used delta. So this actually is really, really nice. Then we're going to switch gears. Well, we're going to do one more and probably our last lossless technique, which is we're going to go with RLE. And I don't know how familiar all of you are with this. This is run-length-encoding. And this is kind of like the easiest compression I could think of. So if you think of this like, if we have a series of numbers, like we have 1, 1, 1, 5, 5, 7, 2, 3. Then what we do in order to run length encode this is we look at how long each run of the same thing is. So in this case, I have 5 runs, right? Here's run 1, here's run 2, here's run 3, 4, 5. And in this case, I just need to say, if I want to compress this, I can say, well, all right, take all these ones, count how many there are. There's 1, 2, 3. All right, so 3 ones. Okay, and then here we have 2 5s. And here we have 1 7 And here we have 1, 2, and then 1, 3. Okay, this is the run length encoded version of this. Now, in this particular case, it's not much smaller than this was. And we could be kind of like evil about how we choose this original, but I can tell you that in a lot of color images, especially in the kind of stuff we're compressing today, these runs are usually a lot of zeros. It's usually like 0, 500 times. And then some more zeros. And then maybe we'll get like a 1 over here, or like a 5 or something. So this compresses really nicely because it's going to say like, okay, this is just 500 zeros, and then, you know, 1, 1, and 1, 5. So these two don't save us much space, but this actually saves us a ton of space. And based on images, this sort of thing happens a lot. So that's and I think it's a pretty good taste of, like, you know, lossless technique that we can get without going too far into the implementation. Never came across it in my studies or work. Wow. Yeah, it's a very old technique, so it's not like but, you know, it's funny how surprisingly good some of this stuff is. All right, so when we're done with all that, we're then going to do like 2 little really simple things, which in our case, they're so back to our pink. So we're still in episode 3, and I have I don't know. Let's go here. So then we're going to move over to clamping, and clamping is all about like saying, well, some colors don't really matter that much. So, hey, what's up, Akshay? How are you doing? Going well, just getting ready to getting all this stuff working. Yeah, and by the way, Okigan, yes, you are correct. RLE gets better if you pre-process with Delta. So, you know, there's different stuff. That's actually kind of getting into what we're going to talk about a little bit later. But actuators don't usually use encoding. Yes, fair enough, Stupak. So clamping is like, we're using 8 bits, you know, per color type. So we're using RGB, and this is red, green, blue, and we're using 8 bits for each of these. So these are 8 bits wide, 8, 8, 8. We refer to this whole format as RGB 888, which is also, you know, more widely known as 24-bit color, right? 8 times 3, because we have an actuary here and Stupak can tell us. So that's great. So with clamping, what we're going to do is we're going to kind of like reduce the range a little bit, because we're going to say that like colors that are pretty close to black, so black would be 0, 0, 0. Okay, or in HTML notation be 0, 0, 0, 0. We can do it as hex. But, you know, basically the same thing. Doesn't really matter. They're just the number 0. So 0, what's the difference between 0, 0, 0 and like 1, 1, 1 and like 17, 17, 17? Not very much. In fact, you'd need to have a really sharp display to be able to see that difference, unless I put them like right next to each other. So what we can do with clamping is we can basically just say, like, if it's less than 20, then just make it 0. So this is really nice because, as Okigan mentioned before, this stacks really nicely with run length encoding. So if we have things which are close to black that aren't really going to add much to our end image, then we can actually just turn them into straight black and then say, all right, well, get longer runs. Okay, great. Then we get that far, and clamping turns out to be really easy, by the way. So, and then just sort of to this example that I brought up over here, we're going to try out we're going to drop a bit. We're going to try to drop the least important bit. And this is going to create a new color space I'm going to call RGB 777. And in that space, we're going to take our RG and B, which was 888, and we're going to make just 1 bit smaller. 1 bit smaller. And the idea here is that if I chop off the last bit, then I'll end up with 777 for my size, but this bit should be like the difference between two colors that are really close to each other. So the idea being that we shouldn't really see much of a difference if we go 777 versus if we go 88 out. Now, this is nice because now instead of using 24 bits per pixel, and by the way, we have to multiply that by the width by the height, so that's a lot of data just to begin with. You know, I mean, we could just send everything in black and white and do 1-bit encode. And then we would save ourselves a ton of work here. But so actually, there you go. That's the ultimate streaming service hack. It's just do black and white. So what we could do here is we could basically say like, all right, if we do 777, we'll end up with just 21 bits instead of 24. So we save ourselves 3 bits per pixel. And while that's not really that big a deal, because if I do this in binary, this is going to end up padding out and some other stuff. But there is a more advanced version of this, which is used quite a bit in gamery. That was a crappy arrow, so I'm going to back that arrow out. I'm not happy there. So we're gonna get more serious with our arrows. And there's a version of this which is referred to as RGB 565. And this is kind of nice because it uses 6 bits for green and it uses 5 for blue and red. And that's really kind of based on some bad artwork. Our eye. And that's because we're more sensitive to green than we are to red and blue. So if we're going to keep some bits, we want to keep them on green and less so on red and blue. Why do we choose these numbers 565? Well, add them up, you get 16 bits. And 16 bits fits into 2 bytes nicely. So we're not going to actually cover this today. I'm just going to like show you this because it's a lot easier to implement. But the same technique that we're going to use applies here. If we just chop off more bits, you know, less here and more here, then we'll end up with RGB 565. Okay, so that is basically what we're going to do. We are going to change colors and we are going to implement all that stuff. We are going to do scale. This is, and we're going to spell too. We're going to do scale down and up. We're going to do delta. We're just going to look at it and we're going to put those letters in the right order. And we're going to do a RLE, which this is probably going to be most of the meat of what we're going to talk about. We're going to clamp, which is really nice and quick, but it causes RLE to get a lot better. And we're going to do RGB 777, which is really more just kind of a tease for what we could do with 565 if we wanted to spend a lot more implementation time. Okay, so that's the plan. It has a line under it, which means that it's serious. So, okay, let's get to coding. Enough talk. Chat, let me know if there's any questions about any of that stuff that kind of came up. So we're in the compression segment and we're trying to go for max quality with the least amount of bits. So, and I'm not going to recycle this terrible joke over here. So, all right, this is exactly where I left it off last time. We have our episode 1 or episode 2. You can catch those on Twitch. I'm going to move them over to YouTube later. But we're going to start in exactly the same place. But I want to try to keep the code like as it was at the end of the episode for when I check it in later. Okay, so let's just copy this over to E3. Let's go into our episode 3 and we don't need the drawing part, but let's go into screen, and this is sort of the code as we left it. I have changed nothing. If I've changed anything, call me on it because there should be nothing different from the last time. Great. So question coming up here is compression algo dynamic based on users' TV? Like if users have crappy LCD versus OLED in practice? The answer is it really depends on the streaming service, Stupak. So a good streaming service, the answer is definitely they are different. But it is a little bit difficult. I shouldn't really just categorize that as good and bad. It actually breaks more along live versus not live. Like if you're doing a non-live streaming service, you have a lot more time to do compression, so you can be really careful about tuning your recipe for like different classes of devices. Versus if you're doing live, something more like Twitch, you really can't do that. You know, the one TV will look better than the other, mostly because of like signal resampling, which is really an advanced topic that I don't want to get into. But the short version is like, if we built a really complete, in our series, we're only building for one device, which is this browser here. And we're building for Chromium, and that's it. But if we were going to do a really solid job with this, a professional product, we would then go and start dealing with all of the different devices that are out there, and not one encode per device, but we would take them in sort of classes. Like, okay, this one has sub-pixel rendering, or this one has you know, a wider color range. You know, it has HDR, or this one has, you know, anyway, different resolutions. So that's more of an advanced topic. We'll get to that later after the show, if people are interested in it. Okay, so what we did here, which somewhat unbelievably worked in a short amount of time. It doesn't surprise me at all that it works. It surprises me that it works from live coding on stream in a short amount of time, because I've been coding for too long. But just to show you kind of the state of affairs of where we were, this was our video player, which is currently not showing anything, so we're in a pretty clear green field here, except I guess I should call it a black field. And we were throwing a little thing. It's looking for a fave icon. We're not worried about that. Okay, so this this was based on having a encode of one image. And so if I wanted, and we're doing one video that was 30 seconds long, so if I want image 123, this is what it looks like as we left it at the end of the last session. Now, this is in our JSON format. Every one of these corresponds to red, green, and blue, red, green, and blue, red, green, and blue. And you'll notice these really long runs of the same number, which is why I wasn't kidding. We're going to get a lot of stuff out of RLE. Now, you'll also notice that all of this stuff is pretty much black. Actually, everything that's on this screen so far is probably beyond our easy visual perception. So all of this, once we add clamping, all of this is going to just turn black, and it's going to run length encode into one nice thing. And that's, we're going to stack these compression techniques as we go. Okay, so where were we with the deltas? That was, so the routine that I just showed you, that was this. All we did was we opened up the image after we, you know, unrolled our video into a series of images, and we flattened it so that, you know, the RGB was just here. Otherwise, they would be in subarrays. This would be a subarray. This would be a subarray. And we then just dump it out. So this is the simplest image format I could come up with. It has no header information, which is a little bit problematic because we don't know what size this is. We don't know how many of these pixels correspond to one line just looking at this. I mean, we would have to try to guess. So a normal image format would have this, but it would also have a little bit of header information to tell you, oh yeah, this thing is 240 pixels high and it's 426 pixels across. We're just going to do that by convention at the moment. We're not too worried about like commercializing this image format, so we'll just do it by convention over specification. All right, so that's what this did. This was a slightly more advanced version of it, which basically just took a starting image. In this case, it always took the image 1, but we would really want this to be whatever the image was before this, which we pass in an ID, and I'll just call it because it's simpler than explaining it. And it only is going to calculate what's different from image 1. So this was our delta encode. And it's showing me all of the pixels that changed since the first frame. But I don't really want all of the pixels that changed since the first frame. That made a more dramatic example when we looked at it. But really, I just want all of the pixels that changed since the image before it. So if I do that, you're going to see most of these numbers are going to disappear because each frame in a sequence changes very, very little. In fact, I just saw a few Yeah, there are a few pixels that changed. So, when you're doing 30 frames a second, like very little of the information is changing from one to the next. I'll file a patent so patent trolls to come after you. Nice, Tupac. Okay. So if they're going to try to patent JSON encoded images, I worry for humanity. But anyway, that aside. So great. This works. This is very simple. All I did was I just, because Python, actually, it's simple. It's harder in other languages. The reason it's so simple is because I open the image. I take image 1 here. I turn it into an array. I open image 2, which is whatever was specified up here, and now I just change it so it's the one before it too. And I turn that into an array. I'm just going to change this back so that, we debugged that in the last session. I turned that into an array. And then what I did was I XOR'd the two. So I just want the bits that need to move to go from one to the other. And that's nice because XOR, you can just keep XORing. It's idempotent, basically. So if I keep XORing, I'll end up with the same thing. If I take something and then I XOR it and then I XOR it again with the same thing, I end up with the original thing. So this is lossless, like I said. I can reconstruct exactly the original image from it. Minus the the fact that JSON could play with the formatting a little bit. And, a space could be added here and it would still technically be valid JSON, but it wouldn't really be lossless. So, all right, for the pedantic people, I'm on to you. Okay, so that's kind of what we did at the end of that session. So if you want to see those implemented, I highly suggest checking out episode 2. But as you can already see, this is part of why we're so interested in run-length encoding. You see all these beautiful zeros? Thousands of zeros. That's going to turn into just 2 numbers. How many zeros and the number 0 if we run-length encode it. So we're going to get quite a lot out of that. Okay, well, that brings us to our next topic, which is run-length encoding. So this stuff was, nice and easy. There's one little nit I should probably mention, which is that right now this is just an image format. So this JSON that's coming down, it's just an image. So to be a video, I have to just send a series of images. Right now I'm sort of requesting them one at a time. I thought that was simpler to see. But if we wanted to actually make this a full video format, we would have to add a little bit of extra stuff to say, like, this is a video, these are the images, and this is either a delta frame or it's a regular image frame, so that our program in JavaScript would know what to do with it. Do I need to apply it to the previous image, or do I need to just reconstruct it from scratch? So there's a little bit of metadata I'm sort of skipping over, but we might get to that if we clean it up in the end. Okay, so another quick question. So will this only send an update when the image changes? Like, if JSON was all zeros, would you need to send that update or not? If it was that would be another metadata item. Basically, we would need to add a 0 frame to say there's a frame here, but there's nothing in it. And then that would tell the client, like, okay, we need to do that. And by the way, we're live encoding this right now. So like we're encoding it as the client's playing it, which is actually more of a live thing. In our service in CSGFlix, we're going to pre-encode. So we already know what the video is going to be. So we can actually encode it ahead of time, and we can just put the encoded file on the server. So we don't need to do any of this logic live. I'm just showing it to you live just for simplicity. We can encode ahead of time. Okay, so how do we run length encode? Well, it turns out we need to build a routine to do so. We need to have a run-length-encode routine. And what that's going to do is it's going to take an array, and that array, I'm just going to make this valid Python so that I don't kill my server, which is still running. It's going to take this array, and it's basically just going to run through, and it's going to count how many zeros are there until, or well, it's gonna say, all right, it's gonna take the first element, which in this case is 0, and then it's gonna say how many other elements are there that are exactly the same. Okay, so it needs to basically kind of scan ahead and say, where is that? Now, because I chose Python, I get to use Python. So we're gonna do this the incredibly simple way, which is we're going to use built-in stuff that's in Python. So just to show you, this is straight Python. I'm not using anything in the virtual environment. So let's say that we had an example image which had like 17, 17, 17, well, I think we'll comma, 17, 17, 17, 0, 0, 0. So the first one is slightly black. The first pixel is slightly black. The second pixel is totally black. The third pixel is totally black. The fourth pixel has maybe some ones in it. All right, so this is going to be just a little piece of what our image encoding looks like. So if we run length encode this thing, we want to end up with 3 17s, right? So that's, you go 3 17s, then you do 6 zeros, and then you do 3 1s. So that would be the run length encoded version of this. And by the way, the run length encoding is not really a standard, so I could put the number of repetitions, and this is the symbol. I can put the symbol first and the number of repetitions. Just adopt one convention for your product. Don't flip between the two. I think the more classic version is you put the number of repeats and then you put the symbol. So I'm going to use that for today. Okay, so if we build this routine correctly, this is our output. We go from this thing as our source to this thing as our output, and then we've got it. That's our run length encoded. We're going to need to run length decode it in JavaScript, so we're not going to worry about that in Python. Okay, well, turns out Python has iteration tools which help with a lot of things, and they're built right into the base Python library. And yes, I am pitching you straight JavaScript devs to also have a little taste of Python, but let me show you why sometimes it's cool. So from iter tools, let's import group by. And group by is intended to work exactly the way you would think with a database, except we're going to misuse it a little bit. We're going to say, I want to do a group by of, and we can, by the way, we can look at what group by does. Group by takes an iterable. In our case, it's going to be this array, and key, that's up to you. We're not going to worry about that. And what it does is it will return something which has keys and groups. And keys in this case are what I'm referring to as symbols. And groups is how many are in that, which is basically free run length encoding, if we're careful. So why don't we group by A, and it's going to pop out an iteration object, which I can just cast, and I'll end up with, this is what it looks like. Well, I have 17 of this iteration object. Then I have this iteration object, 0. So this is, sorry, it's not 17. This is symbol 17. And it's got this many. And then it's got symbol 0. And it's got this many. And it's got symbol 1. And it's got this many. So the only real issue is I just got to get rid of these grouper objects. I just have to turn them into like how many are there. And if I look at one of them, let's just break this apart. Let's say for entry, actually I could say like, you know, name, you know, the name of the symbol and the group thing, this grouper object in group by of A, print name, which we already know is like 1701, and also take this grouper object, which is another iteration thing, and just turn it into a list. List of group. Wow, look at all that work it does for us. We have 17, there's 3 17s. We have 0, there's 6 zeros. We have 1, there's 3 1s, which is, if we look up, exactly what we want. So there it is. That's like run length encoding in like 3 statements. So, Guy, how did you know? So the only thing that we have to kind of watch out for is we just have to say this is actually an array of the number of entries. So I don't want an array of it. I just want how many are in that array. Like just tell me like there's 3 17s. there's 6 zeros, there's 3 ones, and then now I've got kind of the right thing. And if I reverse that order, like I just said, like so that we put the repeat and then we put the what the thing is, we get exactly what we specified before, which is we want 3 17s, 6 zeros, 3 ones. Done. Great. See y'all later. Stream over. So all we have to do is just take this thing and wrap it up into our endpoint. Okay, so let's do that. Let's. I just copied exactly what was in there, except it's not called A here, it's called array. I know I'm not naming things very well. And hey, what's up, cowboy? How you doing? It's so easy with Python. Honestly, though, how long would it take to make this in C++? Stupak, if we get through this series, I'll code it for you in C++. We'll find out. I mean, it's not, run-length encoding is not terribly hard, but it is something that, like, without this operator, I implemented it the other night, and it was like 17 lines. That was still in Python. In C++ with a little bit more memory, it's probably a little bit longer than that. But I mean, it's not like thousands of lines. I mean, it's like max, it's probably like 30 lines. So, but anyway, yeah, let's do it. So we're gonna do the RLE of the array. So at the moment, just to stay simple, let's start with the full image here. And so this is a full original image. So we want to see like 3 17s and then 3 8s and then 3 9s and then, well, some 6s and a whole bunch of 9s. So let's see if we can get that output. Okay, so how do we do that? Well, this is the routine as it is. So this just gives us the regular array. So I can just pass this to RLE encode and we should be all right. So let's RLE encode I1A. This needs to be turned into, this is a NumPy list, so we just need to turn it into a regular Python list. And then let's just wipe out the result. And this is no longer valid because now we're not returning that thing. We're just going to return the result itself. Okay, so we do that. And group by is not defined because I forgot to import it. So I need to import from iter tools, import group by, and we do that, and we get null. That's nice. So there's programming, except because I printed it out, didn't I? So I don't really want to print the thing out. We need to have a result here. So let's yeah, let's get a result. So I could actually take all of this stuff and append it. You know, that would be like, you know, the really non-Pythonic way to do this. But if I just make this an array and I say result.append this stuff here, which would be I want the number, which is the length of the list of the group, and the name, which is whatever symbol it happened to be, and then I return this result. Well, we do that, and append takes 1, but I'm going to turn it into 2, yeah, because this is actually a subarray here. So I'm just going to append a little subarray. There we go. All right, so it's 3 17s, 3 8s, 3 9s, 3 6s, 612 9s. So there we go. That's our run length encoded. Now, the only thing I don't like about this is we're including all of these as subarrays. So let's not do that. You know, let's be good. Let's be good people and not pack our JSON with unnecessary stuff. So the way we could do that is basically just split this into 2 statements is the simplest way to do it I can think of. The better way to do this is to use a for-in, is to use a comprehension, but I don't want to be too Pythonic on this stream, so let's do it kind of something that's friendly to JavaScript dev. Okay, so yeah, hey, what's up, Korean American Barbecue? Yeah, streaming service from scratch, Mr. Demon Wolf. So this is our image format that's now run length encoded. Done. 600 nines, 1,266 zeros. That's it. If I want to be a little more Pythonic about this, I could, well, whatever. We'll clean it up later if we care. Okay, so now our next question is, how do we know if it's right? Right. So before, now I wasn't actually showing this thing displayed. So let's get that image displayed over here. So let's split the screen. I'm going to put the JavaScript back on for everybody, the JavaScript devs, be happy. So here's the JavaScript we wrote in the last stream, just straight boring JavaScript. And we wrote this function show image array. And all it really did, we drew on an off screen. Don't worry about the off screen. Just basically, we're going to draw on this black thing, this black canvas. And we expanded the format that we got because unfortunately, JavaScript uses red, green, blue, alpha. And our alpha value, we just make it the maximum value, 255, and it'll end up being a basically we want the pixel to show up. We're not doing any fading effects. We've pre-computed the values we want, so we don't need to actually send alpha. Or I could just send 255 for every single pixel. And so this is basically the part that displays it. So this should be the only thing that I really need to change. And I just have to basically account for runs of numbers in that part. So Spartan grader. No more JavaScript. Hey, we're in the browser. We got to be JavaScript. I mean, I actually did scripting a little bit on the first stream, and I got a little feedback like, don't do C, please, some guy. So I'm going to do some JavaScript. Yeah, I don't know about JavaScript. It's the best thing ever made, but it's the thing that we're going to use because that's what's generally accepted in the browser. Yes, yeah. No trolling, Mr. Demon Wolf. Yeah, why don't you see how many lines you can do run-length encoding in JavaScript? And then we'll talk. I mean, I really like having this like group by, this does almost all of the work. And I can actually turn this into a comprehension and do it in one line. So it's really a one-liner. But okay, getting a little far afield. So basically, I'm just going to snag this thing. But well, you know what? I don't want to change it. Let's not change it in the display. So for right now, let's just get our image as it was. So this is our normal image function. So here I'm calling, this is not the normal image function. So let's just put this back to normal for a moment. So let's get rid of the run length encoded version. We're run length encoding, but we're throwing it out. So here's our normal image. And by the way, good tip, start from a working version before you get crazy. Okay, and I'm just going to uncomment this image display that we did in the last session. So here, this is for showing delta images. We're not going to worry about delta at the moment. So we've downloaded image A, like some particular image. We can make this 1, 2, 3 so that it works on what we were looking at. And let's just display that. So show image array of this thing. It's just we extended it so that it had to be a context as well. So this is, you have to specify which context to draw it on. So that's basically, I want to draw it on the top one, which is called CTX. So let's show image array on CTX of this image that got returned from the server. All right, so we do that and we get our image back. That's what it should look like. Okay, so why do you draw off screen? I covered that in the last session, Korean American Barbecue, but basically the idea is that originally we started by drawing on the screen. And as we're changing frames in our video, sometimes the video plays the part that we're drawing on. That's called racing the beam. So we're drawing and it's displaying, and then that ends up with visual tearing. So we end up like, kind of screwing our video up a little bit. So the better thing to do is you draw off screen, get it all right, and then pull the whole thing over real fast. And in underlying platforms, you would actually just switch. You would switch buffers and say like, okay, use video memory, draw from here, video memory, draw from here. So that would be double buffering. You could triple buffer. Depends how much video memory Yeah, you catch up on the other one if you're curious about that. What's your views on Microsoft? I'm not going to answer that. Unicorn Glorious TV. That's Microsoft is Microsoft. So I'll be tautological about it. All right. So we're showing our image. That's all cool. So now we want to display the run length encoded version of that. So let's build a quick little function, which is going to basically, this is displaying this format. So here we have it all unrolled. So if there's 3 17s, 3 8s, we're actually displaying all of them. But we really want to switch over to the run length encoded version that we just created, and which looks more like this. So there's 3 17s, there's 3 8s. This is quite a bit smaller if we look at it. And by the way, just to give you a sense of how much smaller, let me I'll just hit this so you can see. We're going to take this thing and we're going to send the result to word count, which is going to show us that this is 133K. This is the curl output, but it matches with what we see. There's 136,000 bytes in the output. That's the run length encoded version. If I do the version that we had before we run length encoded, wow, look at that. We went from 931,000 bytes to 136,000 bytes just by doing like 2 lines of Python. So this is, despite the fact that the technique is very simple in the compression world, it's actually amazingly effective. So we went from a 909K image size to 133K image size. Now I know it's JSON, so I'm not too worried about how much K it is yet, but that is something that we could get to a little bit later. Oh, raid, Primogen, I didn't notice you raided. Thank you very much for the raid. I appreciate that. I saw you were here. I didn't, oh man, I got to get a notification. Twitch noob. And Frad, thank you for the follow. I don't even know if Primogen's still here. I'll have to tell him later. I know platform I use to host my own stream uses index M3 U8. And this kind of same stuff. Yeah, that's an MPEG format. So we're the U8 we'll get to that a little bit later. Creates a buffer on the client, downloads, and then downloads the. Yeah, that's exactly. That's getting into something a little bit different, but related. In that case, we're drawing on the screen. We're racing how fast the screen is drawing, but we could also download in the background like the next few frames and have them ready to go. And then we could actually build better timing and better synchronization. So but the two concepts are definitely related. Yeah, he raided because there were somehow 7 people bots viewing his offline channel. Wow, he is really popular. I mean, but Stupak, I will definitely thank him a little bit later. Or if one of you is in his Discord, please message him that he's wonderful and thank you. So great. Let's keep going. So we're going to build our run length decoder, which is going to be in JavaScript. So we're encoding in Python and we want to decode it in JavaScript. We know that we're saving ourselves like 9 times the file size. I mean, we're going from like 909K to 133K. I mean, it's almost 10 times savings just from that one change. So, yeah, I know big streamers, even when it's offline, they have like 5,000 to 10,000 people just lurk. Yeah, I mean, I'm guessing people just leave their browsers open, or maybe they go, "Oh wow, he's broadcasting again, Primogen. I didn't know you were streaming. Wait a minute, who's this guy?" So, I don't know. When any of you figure out Twitch, let me know because I'd love to know. Okay, and because we're doing video encoding, I thought I'd be coffee cup appropriate today. Just saying. Okay, so right, let's get back to the fun. So here we're going to pass an array in, and our goal is going to be to decode this format. So when we see 3 17s, turn it into 3 17s. So in this case, we have sort of like something that looks like an array of 3 17, 3 8s, on, and we want to turn that into an array that looks like 17, 17, 17, because there's 3 of them, 8, 8, 8, and so on. So this is our goal, is to turn this into that. oops, I could make that more visually appealing with an arrow. There you go. So this is the goal of our RLE decode. Okay, like me, I have a bot. Excuse me, you're a very intelligent bot, Mr. Demon Wolf. Plex Mug, like Plex Media Server. Yeah, you know, a lot of Xflix people went over to Plex. So, yep. So, same cup of coffee, everybody. So, yeah. Yeah, you're definitely a troll bot. Okay. Well, troll me if I get here. Let's see how this goes. So, what I'm going to do is I'm going to build a result, and we need to basically create this array out of this array here. So, basically, let's just run through it. So I'm going to use a regular for loop iterator for this. So I is less than the array length, and normally we would just do like I gets I plus 1, except today we're going to consume these in chunks of 2 because we want to take the number of repetitions and whatever the symbol is at the same time. So we're going to jump up by units of 2. We're going to just assume that we're being passed a valid array. I mean, you would actually have to check, like, is the thing even, and, you know, whatever, but, you know, doesn't matter. We're going to assume we're passing ourselves good data. A real streaming service would need to deal with this. But, okay, so what we're going to do is we're basically going to say, if we pull a number down, so our first, basically, number of repetitions, that's not a good variable name. Let's just say like repetition count. Naming is the hard part of any program. So let's say that the repetition count is, and here I'm actually, I'm passing along an array. So I'm going to say it's array sub I. It's the first entry. We get the repetition. And then we're going to get the symbol, which is going to be array sub I plus 1. And so we're going to read in like the 3, and then we're going to call that repetition count. We're going to read in the 17, and we're going to call that the symbol. And we're just going to basically stick that many into result. I'm going to do this very naively, which is, you know, we're going to build another counter called j, and we're going to say j is less than repetition count and increment j. Then we're going to say results dot push, you know, just add to the end of the array. I know this is horrible on the memory allocator, but you know, you would pre-allocate this with an array buffer if you were doing the right thing, or you would actually just build the image if you want to be really performant. So we're just going to push the symbol. So this little inner loop is going to run as many times as there's repetitions, and each time it's just going to push the symbol onto the end of the array. And we're just going to return that. So count the number of prior counts. Yeah, result out of, yeah, this Stupak, stop showing off the Python. I know this would be really simple in Python, but we're doing JavaScript now. So we're going to just unroll this thing into just a classic loop. We could get fancy and use like array, you know, rep, you know, I don't want to get fancy. Fancy's later. Okay, so theoretically, if we just take I1 and now we call RLE decode on it, I could actually just pass that right here. I could say RLE decode I1. Wow. We're going to get some crazy stuff. Now we're getting into some fun video things. Okay. So this, yeah, that's the good stuff. Okay. So I think, yeah, I'm pretending that the original image file is run-length-encoded, even though it's not. So let's fix that. Hey, look at that. I really liked that. That was kind of very artistic. You know what? We should really poll at moments like that. Like, who thinks it's going to work? So, I'll get better with the polling, but yeah. Okay, so well, let's get rid of that craziness that we just showed up. Although it is kind of pretty. Maybe I'll make that my icon. All right, so we run length encoded this thing. Done. Okay, well, let's go look at our plan. I mean, that's in a nutshell. That already cut down our size like a factor of 9. So that's a pretty big deal. I mean, for compression. So now, of course, this was what we would call very compressible. But anyway, I'm happy with it. It's just a couple lines of code. All right, so where were we? We just did, we looked at delta very briefly in the last session. Scaling, I'm going to play with in a moment. So we just did our run length encode, and let's do a little clamping. And clamping is fun because most of these values that we're looking at, and I'm just going to go back to the non-run length encoded version of this for a second. Most of them, in this case, these are all pretty much black, which if I look at the actual image, I mean, it should be black. These are all related to compression artifacts from MPEG-4. So they're not actually real. And in our case, I'm going to say that anything less than, I don't know, 20 is just going to be black. Let's just clamp it to black, because all of these things, I don't know how it's showing up on your screen, but I mean, they're pretty much showing up as black on my screen anyway. We're looking at the first row. That's black. This row's black. I mean, we don't get to any like business until around here, but again, different types of shots are going to encode differently, but for now we're staying with this simple example. I have the rights to my own video, so I can actually use this on a stream. All right, well, let's just before we return this list, right now we're sort of we're run length encoding the original list. But before we do that, let's clamp it. And I'm going to use a little bit of Python beautiful magic to do this, because I can clamp in one line in Python, which is I'm going to use NumPy for this. In the image1 array, at every single location in that image, at every offset where the value is less than 20, I could do less than or equal to 20, then just set the value to 0. So if I look at the non-run length encoded version of this, which is what's currently displaying, this should set all of this stuff to 0. Okay. One line of Python. See, and now these values, these kind of stand out. This is probably where I'm drawing the CSGFlix. So this stuff, mostly 0. So what do you think this is going to do to our run length encode? So right now our file is pretty much the same size. I mean, these zeros are slightly shorter than 255 if they're strings, but what do you think this is going to do when we run length encode it? Like I said, this stuff stacks. Well, it turns out we're already run length encoding it. All we have to do is just return the run length encoded version. Wow. 8,303 zeros, followed by 125, followed by 2 zeros, followed by 1. So that, and you can tell by the scroll bar that there's a lot less data. But let's be quantitative about it. Let's go and look. 59K, and even curl switched over to showing bytes at this point, because now we've gone from 909K to 133K with the run length encoding, but once we added clamping, we're down to 59K per image. So that just got pretty good. So like I said before, these compression techniques, they stack a lot of them. Some of them don't stack. Like you can't run length encode or run length encoding. It probably isn't going to work, but you can clamp and then run length encode. If I did that in the other way, if I run length encoded and clamped, that would be crazy. But hey, what's up, Marco? We're doing a little, we're doing some compression today, and I just did a little Python magic. So if I go and I reload this page, I get almost exactly the same image, but now I'm literally from 900K down to 59. It's amazing. Okay, so clamping turns out to be really good. Like I said, it would be nice and easy, so I thought that would be sort of fun. Okay, well, can we do a little bit better? I mentioned one other little trick that we could use, which is, actually I mentioned two others if we go back to our whiteboard. So this, we just implemented clamping, and that was sort of dirt simple because Python. But the idea was really like, you know, if, and I went and hid my pen, but you know, the idea here on clamping was if, you know, if like, you know, a particular pixel is less than, you know, 20, I think I did less than or equal to, then just set it, just make it 0. So that was our basic clamp. And it doesn't really matter if you do this in Python or JavaScript or whatever. It's still a very quick to implement kind of thing. And it stacks really nicely with run-length encoding, because once you've clamped most of the values that are close to black, then, you know, you're going to get much longer runs of numbers, especially around zeros. Okay, so let's take a look at this one. This one's a little bit more fun. So not that, although I really like how easy the other ones were and how well they worked. So in the case of RGB 777, we have, and I'm going to be really nice and colorful for this. So we have our red bits, we have our green bits, and we have our blue bits. Okay, and in this case, we had 8 bits for each. So this is 8 bits wide from here to here, and here to here, and here to over there. Okay, now if we're going to throw some of these bits out, which bits are we going to throw out? It's sort of like if we were looking at a number, like if we looked at like 256,724, yeah, there were 256,724 votes on a particular issue. You know, nobody really needs to know this. In fact, they probably don't need to know this, and they're probably okay if you just sort of round that. So if you just said there were 250,000 votes approximately, like that is really kind of good enough for that type of measurement. So if we can apply the same sort of thing over here, that these numbers that are sort of on the left, they're the most important. And to borrow computer science terminology, we call that the most significant. And that's kind of important because they're the ones that affect the overall value of the number the most, as opposed to these numbers over here, which are also called the least significant. And by the way, bad that I used voting there because your vote matters. But let's change this to number of polls I've run in my stream. So, okay, well, these numbers, they don't matter as much. And when we're talking with each other, we sort of automatically compress that anyway. So we refer to these as the least significant or least important in terminology, sort of more English terms, or in more computer science terms, more least significant. Now, in this case, these are all digits, right? So this is the most significant digit, and this is the least significant digit. But we're not using digits here. These are not 0 to 10. These are, well, 0 to 9. These aren't 0 to 9. These are either 0 or 1. And we refer to a binary digit, if I can spell, we refer to a binary digit as a bit. So in case you were ever wondering what that came from. So we have, again, laid out exactly the same. We have a most significant bit and we have a least significant bit. And just corresponds directly to this most significant digit, least significant digit, except we're using binary for it. So in our example, that's over here. So basically, we want to drop this stuff. We want to take these and put them in the great bit bucket, in the sky. So sorry, bits, you have to go. We're going to get rid of you. And the way we're going to do that is we're going to take all of these values and we're going to shift them over one. We're going to take all of these values, shift them over, all of these values, shift them over. And then what we'll do is that'll be our compress step. And then we're going to decode it with our decompress step by shifting them back. So here we were shifting stuff over to the right, and here we're going to be shifting stuff back to the left. That corresponds to the binary operators shift right and shift left. So great. Be nice and quick. It's circled, bit confirmed. Yeah, bit. I can't tell you which I they chose there, by the way, but okay. So this should be nice and simple as well to implement, hopefully. So in our case, what we really want to do is, excuse me, I drink a little more coffee here. Okay, so in our case, we have this array kind of in the wrong format. Like right now we just have a flat array, which is what we want in order to be able to send. But we've lost all of our information by the time we've run length encoded and clamped it. So this is our clamp step here. And this is our RLE step here. So I'm going to just comment both of those out. So we're not going to return that back. We're going to go back to our normal, like we haven't messed with it yet, image that's in JSON. Okay, well, what we want to do is for each of these values, we want to shift it over. So the easy way to do that is just shift it over. So let's do that. I haven't tried that. That might actually work. So in this case, I want to take the I1A, and I'm going to turn this into just a normal, well, it'll turn itself into a normal Python array. So if I say for every value in I1A, then I'll give you a little bit Pythonic about this. Then take X and shift it over 1 bit. Okay, so if I take that and I make that, I'm going to turn that back into a numpy array because it's going to turn it into a normal Python array at that point. Then I should be able to just reassign this and the rest of my code should work fine. There you go. So those 17s, if you shift them over 1 bit, they become 8s. Yeah, that makes sense because 8 is equal to, yeah, that's a 1 in the 7-bit and 1 in the 1-bit and the 0-bit. So that, yeah, I think that's good. Yeah, wow, that was a lot simpler than I thought it would be. So I'm doing a little extra just to turn it back into a numpy array. And the reason, numpy array. And the reason I want to do that is because I want this operator to still work and I want this operator to still work. So if I don't change the fact that it's a numpy array, then I don't have to recode anything. But there you go. Now you'll notice our run got even longer because things that were kind of close now actually ended up translating themselves over. We're also working with, we have less range because before we had an 8-bit range is 0 to 255, but now we're dealing with a 7-bit range. So we only have from 0 to 127. So the numbers are all going to be smaller by nature, but it's just slightly less bits. So that's our RGB 777. And just to make sure that that worked, all we need to do in JavaScript is we need to shift it back. So where's the best place to do that? Here I'm just doing an RLE decode. You can't recover the clamp because the clamping was lossy, but the RLE was lossless. So in this case, this is another lossy transform. Why don't we work on the RLE decoded version of this array? So let's just RLE decode I1. And let's, we'll create a new function here, which is going to be called RGB 777 to, actually, you know what? I know the simplest place I could do this is actually, I could just change it in the show image. So when show image comes up it actually looks at every single pixel already. So all I have to do is just take this thing and shift it back over one. And I get exactly the same thing. Now, this is 1 bit less of fidelity on every single color value. So now I'm using 21-bit color instead of 24-bit color. So I'm saving myself 3 bits per, well, yeah, I'm saving myself 3 bits per pixel. Wow, man, it just worked. I mean, of course, I knew it was going to work, but if I, by the way, did not shift it back over, you'll notice it looks a little bit more faded out. And that's because I've now pushed it. I've pushed numbers that were from 0 to 255. I've compressed them to 0 to 127. When I expand them again, I'm never going to get that original bit back. I don't know if it was a 0 or a 1, but I'm going to get it to be in the right size range. So if I display it now, it all just shows up as sort of faded out. But if I expand it back, then yeah, there you go. And what do we do to the amount of bytes that we passed in the wire? Well, we probably didn't change it very much. Actually, we did. Wow. Yeah, because the numbers are all smaller in JSON. But so now we're down to 46K per image frame. And that's nice, but what's really, like I told you before, that was using, we went from RGB 888 to RGB 777, 7 bits for each component. But if we go even further to RGB 565, then when I turn this into a binary format, this is going to fit into 2 bytes, which is really nice because that's 5 plus 6, 11 plus 5 is 16. So I'll take my 24 bits and I'll turn it into 16 bits. I'm saving myself a lot of data being transferred. So this 565, like I said, is it's better, but it's not something that we're going to do today. Okay. Well, there's really only one thing left that I said we would touch on and we didn't, which was scaling. And in the case of scaling, and I don't want to push that too far, but I don't want to actually implement the scaling, which is actually a case of resampling, which gets into frequency transforms. Instead, I'm going to do the really simple version of it, which is I'm going to let the browser do the work for me. So I'm going to keep my off-screen canvas kind of the same. So it's still going to keep the same size, which is our off-screen canvas is defined as 426 by 240. So that was defined over here. And when I draw it onto the real canvas, we could just size that element up. And I haven't tried this, so let's see how that works. I'm gonna XML comment this out, and let's figure this out. So this would be 240, so that would actually become 480. And 426, I don't want to do any math. It's 852. Okay, so if I do that, yeah, okay, I'm still drawing into the bits that are on this size. So that actually won't do the job for me because I'm actually blitting the thing directly. But what I could do is at this stage, I could actually resize it. And I could say like, okay, just blow this up for me and we'll just let the DOM do the work. So in this case, if I really want to cheat, so that we do it today, we could actually just say like, let's take the canvas element, which in this case, yeah, see, I built this to use it for different, let's not do it. It's going to be a little bit crazy. I'll leave it up to you, Chad. I'll see if you want to see it or not. We'll come back to that if you do want to see it. But basically the idea is that we're just going to draw this thing and then we're going to say like, okay, right now we're sort of bit copying the whole thing over. This is doing a put image data. So I could just resize it right there if I wanted to. And I could just say, use this context. We could get the underlying, I think I left that in global scope. Yeah, this is the off context. And we could take we would need to get the canvas back. And with the canvas, we would be able to transform the width and the height back. So, so I could take this, its corresponding canvas and its width, and I could turn it back into 852. And this thing, and I could turn it back into 480. And I think that's the cheapest way we can get scaling to happen. Oh, yeah, no. All right, whatever. I'd actually have to like go and do this the right way. We don't need to actually implement the scale itself. I can tell you that. What we could do is if we took that image data, there's actually there's a routine in the canvas for the scale, which is basically you just have to specify the whole size, and if it notices that it's bigger, it'll actually do the scale for you in hardware usually. But so I don't know. Let's not get into it. It's not really fun. Oh, did I forget to put Python in there, Stupak? Yeah, that's what I get. All right. Well, that's pretty neat. This minus this little part here, which we're not that worried about. This, yeah, that works. I mean, I'm gonna toss that 480 out because we're done with that 480. Basically, the moral of the story is that at the other side, I could just expand it. So I just have to be careful that I'm not directly drawing on the canvas, which, in my case of my image, I think I am. So we could probably get fancy with like off canvas. Yeah, see, I'm going to end up going down this rabbit hole if I'm not careful, which I'd have to look at the MDN for off-screen canvas, because I'm pretty sure you have a routine on there that'll kind of do our... Okay, yeah, you do have a height and a width. And that's because, so this actually would be changing it. Oh, that's what I did before. Oh, all right, whatever. I'll debug it later. That's probably not interesting. Or you could just transfer it to an image bitmap and then use that when you draw it on. That's fine. We could do all sorts of sins in the browser if we want to. Okay, so that's, let's see, scaling, deltas, RLE, clamp, RGB 777. That's kind of it. That already compressed us down to a pretty good size. So I guess the question really from there is, if you wanted a more advanced compression, for example, like the ones that you referred to before in that Mr. Demon Wolf mentioned, or some of the others that came up in the channel, it's actually using these kinds of tricks. So the first is you wouldn't use run-length encoding. Run-length encoding, like this, it worked really well, and I think it's relatively simple to implement, so I wanted to not get too bogged down in building a compression thing. But we could actually use something that uses the deflate algorithm. And deflate this is based on Huffman, Lempel, Ziv. It's actually covered in RFC 1951, if I remembered correctly. Yep, deflate compressed data. So you actually can, this is now off patent. And this is similar technique, except it's also going to add a Huffman code, which is a different technique. But it's going to end up building a code book and looking for longer runs. So in our case, we were just basically saying, how often does this symbol happen? And that's it. And as soon as the run gets broken up, that's it. That's as far as it can compress. Here, we're going to kind of look a little bit deeper. We're going to say, okay, how often does this pattern repeat? And reference it. So build like a code book. Okay, here's a pattern. All right, here's the same pattern a little bit later on. Well, that's just pattern 1. So just put pattern 1 in. And then later on, you could say, okay, that's actually just pattern 1 again. So use that. Or that's another pattern that happens a lot. That's pattern 2. So put pattern 2 in here. So that's like a slightly more advanced version of kind of like this run length encode. And that works better. And that's basically the deflate algorithm is what Zip and gzip, they all use this. bzip2 uses a slightly different version of it. It's kind of like, are you using the 77 standard or the 78 standard? But you can read about that stuff later. One of the nice things about zlib is it's already implemented in JavaScript. So if we wanted to pull in a zlib, this is a pretty fast zlib that's in pure JavaScript. If we don't want to count on the browser at all, we could actually just pull this module in and add it to our program. And then we could actually just, zlib is already built into Python, so I could just import, I can import the compression stuff. And we could get even better than what we're doing now. But I'm already kind of happy with 46K, and deltas are going to be really small using these techniques that we just saw. So I think that's probably a pretty good place to stop. So I do want to say that the best thing, we can use better lossless techniques, sort of like what's in zlib. We can play with bits. We can obviously stop packing it in JSON. We can actually create binary. That'll give us a huge savings right there. We can base our deltas. Right now, our deltas are based on the frame before. But if we allow that to go further, we could just find any frame in a reasonable distance that's similar to the frame that's there, and then just encode that. So if we mark in the start of that frame, like, okay, don't use the frame before, use the frame 3 frames ago, the differences from that, then we could optimize. If we do more in encoding, we could optimize like the minimum delta that we need to pass. And that's basically how MP, that's an MP4 in a nutshell. If we allow that to go, that's switching to, that's called a P frame. If I go if I allow it to go either way, forward or backward, because who cares about time traveling? No problem. Then that's called a B frame, and basically I can say, yeah, just build the delta off those other things. We can also use frequency. So what we can do is we've been working in the time domain. We can transform this to the frequency domain, and we could take blocks and say, well, the average color in this block is this, and so just encode that. That's another way of sort of doing a lossy transform. I could also, I could choose my regions carefully. Like I could use a larger region based, a variable size region. I could probably get some savings there. Wavelet encoding uses that kind of trick. Or I can also say that most video images, they don't just delta. Like delta was literally a pixel by pixel comparison. But I could say that, like, for example, in a fast moving shot where the camera's turning, like if we're doing like a car chase scene or something like that, then most of this image is the same as this image. All I had to do was just kind of like move everything over a little bit and then add the part that's missing. So that's a motion technique. So we could do motion techniques if we wanted to get more advanced. And that's basically modern compression. I mean, it's a very difficult field, but the basics really aren't, like it makes sense. It came out of stuff that makes sense. Okay, Huffman coding is a little complicated if you haven't seen it before, but I'd like to thank everybody who dropped by today for building a streaming service from scratch. Now, what I'm going to do off stream, probably for the next time, is I'm going to actually just pack these things up into a single file. Like right now I have a single image, but if I just put these if I take this whole array here and if I nest it inside a bigger array, then I could say like, okay, this is an image frame, this is a delta frame, this is an audio frame. I could just mark that if I just pack this JSON a little bit more. So I'll do that. It's boring to watch, so I'll do that off camera before our next stream, but it's not going to do anything substantial there. I'll show you that at the start probably of the next stream. And yeah, come back next time. We're going to be doing UI. I mean, now that we know how to build a video format in JSON, we got to pick out what we're going to watch. And so I'm going to take a few of these clips and we're going to build some UI with the kind of constraints that you have to deal with on a real TV. We're going to pretend our web browser is a TV, and we're going to use a TV remote control device of some sort. I'm not going to mention what device we're going to use. Now, we're not actually going to use the power glove. We'll probably use just the keys to simulate using a infrared remote control. But yeah, that's kind of what's coming. At that point, so UI is going to be next, And then we're going to get to the real fun and the meat of how to build this over a real internet connection. Now, we've been worried a little bit, especially with compression, about how many bytes we're sending. Let me tell you that the less bytes you send, the more internet connections and connectivity circumstances it's going to work over. So it's always better to make sure you've got good compression. But once you know you've got pretty good compression, then the real internet poses, it's a playground like none other. And like I said, this is actually probably the largest area that tends to make or break streaming services. And then we'll worry about this other stuff as we get there. So I'm going to stick to twice a week, just format-wise. So we're going to keep going with Wednesdays and Fridays until we get through this stuff. Might need a little break to prep this one, but we'll see as we get closer to that. But anyway, definitely want to thank all of you for coming.